Hello everyone, I'm Yixuan Li. I will introduce our SCCV paper, MatrixCity Dataset. Please refer to our homepage for more details. City-scale scenes neural rendering has many applications, such as aerial surveying, virtual reality. However, collecting a city-scale dataset in real world is time-consuming and resource-intensive. Also, it's impossible to control environmental factors like lighting, weather, and human car cross. This leads that the existing datasets only have a few independent scenes rather than the whole city maps. Also, they only contain single view angle, so we construct a synthetic city-scale dataset, which is much cheaper and can flexibly control the environmental factors. Then I introduce how to collect the data. We built the data based on city sample project in Unreal Engine 5, including two maps, Small City Map and Big City Map. We develop a plugin to generate the camera trajectories. Based on the trajectories, we render images with the best quality. Here are some demos of our dataset. Besides, the city sample project can flexibly control the environmental factors. The bottom figure shows that we can smoothly adjust the light intensity and angle, the fog density and heat. The top figure shows that we can control the presence of moving people and cars in the scenes. These functions allow for the simulation of almost all basic dynamic situations found in the real world, which will lead to more realistic and accurate city-scale neural rendering. Except RGB images, our plugin also provides the depth, normal, and decomposed BRDF materials. These attributes are important for studies on inverse rendering and semantic analysis. While these attributes can be expensive and even impossible to obtain in real-world scenes. For aerial results, we divided the map into 5 blocks based on building height and coverage area. From the table 2, we can see that MIPNOV 316 and Instant NGP perform better, which indicates that both grid-based methods and MLP-based methods can model the block size area data well. Additionally, we found that the high-rise area is more challenging to model than the floor area because there are more occlusions between the buildings in the high-rise area. From the visualization, we observe that current methods cannot accurately model small objects and reflective buildings. For stray data, we first run all the baselines on the stray data of block A and find that all the methods perform much worse than the results of the aerial data, especially for the grid-based methods, which can be seen from the table 3. We analyze that stray data contains much more details, so it's harder to achieve high-quality results on stray data. So we conclude that modeling the stray data of a block size area in a single model is not reasonable and filter across row data to test current methods called block small. Analyzed the results on block small, we find that the MLP-based methods perform better than the grid-based methods. Also, we estimate the depth and normal results on both aerial and stray data. We can also find that the stray data is harder to reconstruct. Also, we do experiments on the joint types of data. We find that the performance of both methods get worse after simply fusing the area and the stray data to train together. This problem is non-trivial and worth further investigation. This is a rendering demo on the area data. This is a rendering demo on the stray data.